the recording. So I think it's doing that. It better be doing that, or I'm going to be redoing this as a recording later. Okay. So similar to last time, except it'll probably only be about an hour, because that's about where I was going to lecture in class today. So it seems like that would be good. I already sent you an email, which I assume you guys got, talking about what the plan is, at least as far as I know at this point. So obviously you'll have your exam on Monday. We'll continue lecturing on chapter 4 on Monday, and then you'll have your exam, and I'll let you know what we're going to do about lab. If you have questions, please, as I'm going along, send a chat message, or feel free to unmute yourself and ask a question. Maybe you guys are more willing to do that since we've now had class a couple times, unlike the first time where we had not had class at all yet. And just so you know, you can mute your video or your audio. Definitely mute your audio unless you're asking a question. And then if you don't mute your video, just make sure you know that everybody can see you. And so just keep that in mind. I'm going to switch over to the other camera that does the packet, and I'm just going to go through the packet like I do in class, and we're going to go through some naming of alkanes and through some properties, and that's all we're really going to cover tonight. I think that's it. I think that we'll go ahead and get started on this. So let me switch to the other camera. All right. So it doesn't seem to focus much better than that, but hopefully you guys can read that, and maybe you printed off the first few pages so you have it in front of yourself anyway. All right, so we are going to now, what's going to happen now for this chapter and moving forward for the rest of the semester, each chapter is going to focus on a particular functional group that we learned about. And we're going to learn how to name them, how to compounds with those functional groups in them. We're going to learn about their properties. We're going to learn about reactions that make molecules with that functional group, and then reactions that functional group will do. And that's sort of the general overview of every chapter from here on out. For the most part, we've got a couple differences, like when we do redox and things like that. But for the most part, that'll be the format of the chapters. And then if you continue on to Org 2, you basically continue on with the functional groups that we don't cover in Org 1, as well as a couple other things. So our very first functional group is our simplest functional group, which are alkanes. And so we've already talked about how alkanes are when you have carbon and hydrogen, and they're all sigma bonds. So you'll have carbon-carbon bonds, and you'll have carbon-hydrogen bonds, and they'll all be sigma bonds. So no pi bonds in there, because these are alkanes, so only single bonds. And so that makes them pretty simple compounds. Now, we have both cyclic and acyclic. So acyclic means not cyclic. So these would be the straight chain or branched chain alkanes, but they wouldn't have anything that forms like a cyclic compound, like a circle type of thing. So we'll use this term acyclic quite a bit. So those would be your straight chain or branched chain alkanes. And all of them have the molecular formula CN H2N plus 2. I'm looking at the wrong place on my handout and getting confused. So this means that however many carbons are in the compound, that's what N tells you. If you multiply that times 2 and then add 2 more, that's how many hydrogens will have to be there every single time. And so once you know how many carbons, you can figure out how many hydrogens. So when you're looking at the naming, you don't necessarily have to memorize how many hydrogens would be on a molecule, because you can always calculate that using this particular formula. Now, this formula only works for your acyclic alkanes. As soon as you add double bonds or other functional groups or things like that, this formula doesn't really work anymore, but it does work for your acyclic alkanes. And they are considered saturated hydrocarbons. And I've used that term before. So when we think of the term saturated, we mean it's saturated with hydrogens. There are the maximum number of hydrogens per carbon that you can put on the molecule. So that's what the term saturated means. When we start looking at double and triple bonds, those molecules will be saturated, but alkanes are saturated. And that's when they have no rings either. So again, this is acyclic. When we get to cyclic, they're not really saturated anymore because they don't have the maximum number of hydrogens. All right, so then the cycloalkanes, so now these are the cyclic ones, they have the molecular formula CnH2n. Notice they have 2 fewer hydrogen atoms than the acyclic ones, and that's because 2 of these carbons have to come back and form a bond with each other in order to make the cyclic structure. So they'll have 2 less hydrogens on there because those 2 carbons have a bond with each other. Yeah, so all carbon atoms in an alkane are sp3 hybridized, and therefore they have tetrahedral geometry. And again, there's no pi bonds in any of these, so that's why they're all sp3 hybridized, and all of them will be tetrahedral. So using this formula here for the acyclic alkanes, we can do a count here of how many hydrogens. So if we had 8 carbons, then 2 times 8 plus 2 is going to be 18. So there would be 18 hydrogens, so it would be C, what was that, 8H18 would be the molecular formula for that compound. If we had 23 carbons, same idea, 2 times 23 plus 2, which would give us 48. So the molecular formula would be C23H48, and we could go on and on and on. So as long as it's acyclic, we could calculate how many hydrogens it would have, and then if it was cyclic, we would use this formula. Okay. All right, so here's just some examples of some acyclic alkanes. So we have our simplest one, which is methane. So that's CH4. So we have a single carbon is going to give us 4 hydrogens, and that's this guy if we're looking at the model. Notice it's tetrahedral, sp3 hybridized. And so we've got a Lewis structure, we got the perspective drawing, the 3D representation, we've got a ball stick model, so we can look at them in all those different ways. Ethane would have 2 carbons, and therefore it would have 6 hydrogens. So here's again a Lewis structure, a perspective drawing, a ball stick model. With ethane, we so for both methane and ethane, we don't necessarily do line drawings because methane would be a dot, and that it's really hard to see that. So we don't usually do that. And ethane, although you could just draw a straight line, usually they don't. It still could be a little bit confusing. A straight line could get confused with other things. So once we get to propane, 3 carbons and then 8 hydrogens, then we see we can do line structures. So now we have this little bend, 1, 2, 3 carbons, knowing that that's going to be filled with hydrogen, so it actually would look like this. And then here's a ball stick model. And then from then on, we can do line structures or Lewis structures or any of our other types of structures for those. But for methane and ethane, we can't necessarily do a line structure. It doesn't work out so well. We're going to go over the naming in a minute. So just, I know I mentioned a few names there. We're going to go over how those work out in a second. Just kind of reminding you of a few of the alkanes. So I was noticing this heading and I was trying to make sense of it for myself. So there's the first 3 most simple alkanes, most simple organic molecules, really. So a single carbon, 2 carbons, 3 carbons. And so it says we're going to also talk about 4 and 5. Once we get to 4 carbons and 5 carbons, then our molecules have constitutional isomers. Methane, ethane, and propane do not have constitutional isomers. But once we get to 4 or 5 or more, we have constitutional isomers. So now we have to bring this into talking about the molecules. Isomers, or constitutional isomers, are isomers that differ in the way the atoms are connected to each other. Later on, we're going to see that we also have something called stereoisomers, but we don't have that yet. But that's why we have constitutional isomers are specifically isomers that differ simply in the way the atoms are connected to each other. And we'll see a different type of isomer later. So once we get to 4 carbons, we could have just a simple straight chain, which is called butane, with its 4 carbons and 10 hydrogens. Or we can have a branched chain that has 4 carbons and 10 hydrogens. And these have the exact same molecular formula. Both of these would be C4H10. But yet you'll notice they're not the same molecule. So therefore they are constitutional isomers of each other. You'll notice that in the straight chain, we can just do the zigzag line, 1, 2, 3, 4 carbons. With the branch chain, we do the 3 carbon, and then we put a branch off of the middle carbon. And so that is another way we can draw C4H10. And it has a different name, but we're going to go over the naming a little in a couple minutes. So, but you can see the names here if you're curious about those now. Another term that you might see come up is normal alkane, or more likely how you'll see it is a little N-alkane. And that signifies a straight chain alkane, so no branching. So if you see the term normal alkane or N-alkane, they're referring to a molecule that doesn't have any branching. So if you were asked to draw a molecule with C4H10 that is a normal alkane, they're meaning draw straight chain alkane. So that's a term you might see come along. So I wanted to make sure you've heard that term. All right, so let's turn the page. Again, if you have any questions, make sure you put them in the chat, or maybe unmute yourself so you can ask and I actually hear you as we go along. So that is, so the one we just looked at is the 3 carbons. There are 2 constitutional isomers when you have 3 carbons in an alkane, acyclic alkane. I'm trying to make sure that you guys can see it, and between the glare and the focus, it's really hard to see. So maybe I'll have to hold the page down. That might be helpful. You don't necessarily need to know the names yet anyway, because we haven't gone over the names, so that's okay. So then what about, so that was, we looked at 1, 2, 3, and 4 carbons in our acyclic alkane. What about 5? And so with 5, again, you can certainly have the straight chain, which we call pentane, which is going to have 5 carbons and 12 hydrogens, C5H12. And now we have 2 constitutional isomers of pentane. So there would be 3 total ways that you can draw C5H12. So 3 isomers of C5H12. And you'll notice the other 2 have branches. This one has 1 branch coming off a chain, and this one has 2 branches coming off of a chain is one way you can look at that. Or you notice that there are 4 carbons attached to a single carbon in the middle. And that might be easier to see with the model, although maybe not on the page with the glare. So again, the straight chain is your normal alkane, and then these 2 are both branched alkanes. So one of the things you want to get really, really good at is being able to look at especially line drawings, but also any other types of drawings or Lewis structures or perspective drawings, and be able to figure out exactly what is it. So you want to get good at spelling your carbons. Is it a straight chain? Is it a branch chain? And especially counting your longest chain. So the example here says, which of these 4, for each of these 4, is it or is it not a representation of 2-methylbutane? Well, you don't know the name 2-methylbutane yet, so we're going to go up here to this, and if you could read that, it says 2-methylbutane. So this is 2-methylbutane. So you'll notice it has a chain of 1, 2, 3, 4 carbons, and then has a 5th carbon coming off of this 2nd carbon in the chain. So we're going to look at these 4 structures and see which of them are also 2-methylbutane and which of them are not. So you want to get used to seeing that they can be drawn in different ways. So your main thing there is going to be to count your longest chain. That's the first thing that you're going to want to do. It also may not hurt to double check your molecular formula and make sure it's the same as 2-methylbutane, but I already know that all of these have the same molecular formula as 2-methylbutane. So the question is just which one of them are still represent 2-methylbutane and which one of them are one of these other isomers. So you would want to count the chain. So notice this is a branch chain. There's 1, 2, 3, 4 carbons in the longest chain, and then there's a branch coming off the 2nd carbon. So that is the same as this. So this, we're gonna say yes, meaning it is 2-methylbutane. Okay, we're going to say no when it's not 2-methylbutane. That way you know what I'm writing here. So then this one, same idea. So we go and count our longest chain, 1, 2, 3, 4. And again, there's a branch coming off the second carbon. So yes, it actually is the same as well. So notice this picture, and this picture are all the same molecule. All they've really done is turn the molecule around. Flipped it over, turned it over this way, turned it upside down. But it's all the exact same molecule, and you really want to get used to being able to see that, because we're going to use a lot of these line structures, and it's going to start to get confusing if you don't get really good at knowing what those structures mean. And then also with a perspective drawing. So again, it looks like we've got 1, 2, 3, 4 carbons in a chain, and then there is this other carbon coming off of the second carbon. So yes, this one is also still 2-methylbutane. So this is just a perspective drawing of this or this. So if I took this and twisted it, it would fit right on top of there. Okay. And then we go to this one and we count the longest chain. 1, 2, 3, 4, 5. So this carbon is attached to this carbon, which is on an end, which makes this the actual end. So this is not 2-methylbutane. Matter of fact, this is simply pentane. This is the same as that one, but not 2-methylbutane. So you have to be really careful, because although you might be expecting to see the other carbon drawn as another zigzag here, they didn't bother to do that. Instead, they drew it down here on this wedge, but it really is still just a representation of this chain. Okay, so your way for learning this is to just look at lots of structures and compare them and be able to count your longest chain. You're going to need to count your longest chain to do the naming anyway, so you want to get really good at that. So this is just to kind of let you know you're going to need to be really careful looking at these structures, and you're going to need to practice. Okay. All right. So, and we're not going to go past that as far as looking at the isomers, because it's just going to keep going up. So notice, I'll start to talk about this chart, and then we'll come back to the sentence above it, trying to get it to focus as best I can. So here's your methane that we looked at with just 1 carbon. Here's the ethane that we looked at with 2. Here's the propane with 3. Notice they don't have any isomers. There's only one way to draw those. But we get down here to the butane with the 4 carbons. And like we just saw a minute ago, it has 2 isomers. And then the pentane, which we looked at just up here, which has 5 carbons, has 3 isomers. If we were to keep going, we would see that hexane, which has 6 carbons, has 5 isomers. Heptane has 9. Octane has 18. If we keep going to this molecule that has 20 carbons, there are 366,319 constitutional isomers. So notice that the number of isomers, the number of ways you can do branching and chains and stuff with these carbons just goes on and on. This is why there are so many organic molecules, and why we spend 2 semesters talking about organic compounds, because this is still just alkanes. We don't even have any other functional groups attached yet, and we already have, over 4,000 molecules. There's the question, do you need to memorize the chart? Kind of, but not exactly. So let me talk about that in a second with the naming. So let me go back here to these 2, and then we'll come back to starting to talk about the naming, which is where we'll talk about what you need to know from the chart. All right, so that is kind of an overview of alkanes, but we're going to have these branches. And when we have these branches, we're going to need to have a way to name them. And we call them methylene groups, or this is a methylene group. Let me show you that. CH2 is a methylene group. So a group of compounds that differs only by a methylene group, like how many methylene groups in there, is called a homologous series. Homologous series. And this in the chart is a homologous series. So again, if it weren't so blurry, it might be easier to see. But this is, if we look at these as just a straight chain, this would be CH4. Maybe I'll do it this way. So here's your methane. Here's your ethane. Here's your propane. Here's your butane. Pentane. Hexane, and we keep going on. So notice the only difference between here and here is one of these CH2 groups. There's an extra CH2 group in here. The only difference between here and here is there's an extra CH2 group. The only difference between here and here is there's another CH2 group. So these are in a homologous series. You're adding another CH2 group with each one. Okay, and that CH2 group is called a methylene group. So this has one more methylene group than this has one more methylene group than that, and we could just keep going on and on and on through the chart. So that's what homologous series means. Let's do example 3 first, or at least part of it, and then I'll come back and talk more about the naming and this chart. Okay, so example 3 is again trying to get used to reading or deciphering the different ways you can draw a compound. Okay, so what they're asking is they're wanting you to start with compound A, and then they're wanting you to compare B to A, C to A, D to A, E to A, to F to A, and they want you to determine, is B the same as A, or is it an isomer of A? So right away, I'm just going to tell you up front that they all have the same molecular formula, but that would be the first thing you would check if you were asked something like that, okay? Because if they don't have the same molecular formula, then they're not identical and they're not isomers, and that might be an option. But I'll just tell you that so we take care of that right up off the bat. So they're either identical to A or isomers of A. So let's look at how we would do that. So this is where we're trying to count the longest chain. So let's first count the longest chain for A. If we go just across the diagonal, we have 1, 2, 3, 4, 5 carbons. But if we go this way, we have 1, 2, 3, 4, 5, 6 carbons. So the longest chain is 6 carbons. And then the question is, so now we've got this branch, which is a methyl group. It's just a single carbon branch. We want to see what number carbon that is on. So I want to number the carbons in this chain. And because we are going to move into naming, we might as well start to number them the way we're going to number them for naming. So we're going to number it, because I could start over here, which would put this methyl group on 1, 2, 3, 4. Or I could start numbering on this side, which would put the methyl group on 1, 2, 3. We want to put the substituent, which is what this methyl group is called, on the smallest number carbon. So this extra CH3 is on carbon number 3. 1, 2, 3. So now when I go to compare B to A, I'm going to count its longest chain. And if it's not 6 carbons, then it's not identical. If it is 6 carbons, then I'm going to look and see if there's a methyl group on carbon number 3. And if there is, it's identical. If it's on a different carbon number, then it's an isomer. Okay, so that's how you would approach something like this. So I'm going to go to B, and this time the zigzag in a line is the longest chain. 1, 2, 3, 4, 5, 6. So yes, it has 6 carbons in the longest chain. I want to number the chain so that this methyl group's on the smallest number. So I'm going to start here, 1, 2, 3. And yes, the methyl group is on the number 3 carbon. So this B is identical to A. Okay. So now I want to do it with C. So I need to count the longest chain. 1, 2, 3, 4, 5, 6. And I'm going to go that way because if I went this way, I would have less. 1, 2, 3, 4, 5. I'd only have 5 if I went up here. And I want to go the direction that's going to give me the longest carbon chain. 1, 2, 3, 4, 5, 6. So yes, this is the longest chain is 6 carbons. And then I want to see if this extra branch is on the number 3 carbon. If I start counting this way, 1, 2, 3, 4, it's on the 4. So I'm going to count from this side, 1, 2, 3. 1, 2, 3. And yes, this one is also identical to A. Notice A, B, and C are the exact same compounds. They've just been drawn a little bit differently. And you really have to get used to that. So then I come to D. My longest chain looks like it goes around 1, 2, 3, 4, 5, 6. Notice it's not a cyclic compound because there's no bond connecting these two. So it's a chain, 1, 2, 3, 4, 5, 6. So it also has 6 carbons. And then I've got this methyl group, the substituent, and it's on the number 1, 2 carbon. The methyl group, the branch, is on the number 2 carbon, so it is not identical. Instead, this one is an isomer of A. So D is not identical, it's an isomer of A. Then we go to E. 1, 2, 3, 4, 5, 6. 6 carbons. 1, 2, 3. Methyl group is on the 3rd. This one is identical. Again, we're going to start counting the longest chain on the side that puts this branch on the smallest number. It doesn't matter which side we start on, so I'm going to start here so it puts it on the 3, so it is identical. And then this one here, the longest chain is 1, 2, 3, 4, 5, 6, 7. So it is not identical. It would be an isomer. And it does have the same molecular formula, so it's an isomer. All right, so hopefully those examples let you know that you have to start practicing and these things. And notice this down here, you need to practice drawing isomers. There's definitely some problems in your homework problems that talk about, draw 5 isomers for this molecular formula or something like that. And something you need to be really, really careful of is that you're not just simply drawing the same compound over and over again in different ways, because these two are not isomers. They're identical. So you can't count these as separate isomers. So you have to be careful that you really do have a different compound or a different way of putting it together when you say it's an isomer, and not just that you've bent the chain differently. If I take a chain, I don't have my bigger chain model here with me, but I at least can take this one. So I can bend the chain like that, it's still a 4-carbon chain. I can bend it like this, it's still a 4-carbon chain. So this is the same molecule, not isomers. And so it can certainly be drawn these different ways. So you need to be really, really careful of that. All right, so that is just going to take some practice on your part. So then the next thing is, and we still have to talk about the acyclic ones, but before I go on to that, let's go back to this table and start talking about the naming, because that's coming up in just a minute. So you need to know, so let's look at the pattern, which again, it's hard to see because it's kind of blurry. Wish it wasn't, but can't seem to make it better. You should notice a pattern where every one of these ends with A-N-E. That tells you that they are alkanes, as opposed to when we get to the chapter on alkenes, they'll all end with E-N-E. When we get to the chapter on alkynes, they'll all end with Y-N-E. So the fact that these names all end with A-N-E tells you that the compound is an alkane. Your carbons are all sp3 hybridized. Okay. Then the next thing you might start to notice is the only thing that's changing is what's in front. And what is in front actually tells you how many carbons is in the molecule. So what you need to memorize is that meth means 1, eth means 2, prop means 3, but means 4, pent means 5, hex means 6, hept means 7, oct means 8, non means 9, and dec means 10. And you need to have those first 10, I don't know you could call it a prefix, but we're going to use the word prefix for something different in a minute. You need to have those those first 10 numbers of carbons and their names memorized. You do not have to memorize how many hydrogens, because that is where this formula comes in, CnH2n. So when you need to know, so let's say I gave you the name propane and asked you to draw the molecule. You would say, okay, A and E means it's all carbon, it's only carbon and hydrogen, and they're all single bonds. You need to know that prop means 3 carbons, because we are going to keep using the word prop to mean 3 carbons. When we have propene, there's going to be 3 carbons. When we have propyne, there's going to be 3 carbons. And I think of prop as propeller, and there's 3 blades. So that's one way to remember it. This is what you need to memorize. So that then you would say, okay, I've got 3 carbons, no double bonds, 1, 2, 3. That has to be propane. And if you wanted to know the molecular formula, you would say, all right, well, I have 3 carbons, 2 times 3 plus 2 is 8, so I'm H8. So are you memorizing this chart? Not really, but some of it. You're going to memorize meth, eth, prop, bute, etc., all the way down to deca, and how many carbons that means. And then you're going to know the formula, CnH2n plus 2, which will get you how many hydrogens. And that's what you're going to memorize. Okay, and we certainly have more naming to talk about, but that's, and don't worry about the undeca or dodeca or trideca. I'm not going to worry about you guys having those memorized. You can see that when you keep going on, we keep having names that equate to a certain number of carbons, but I just need you to have the first 10. I need to cough a second. Are there any questions on what you need to know with the chart? Okay. All right. And then we're going to use that as we go through the naming. Before we get to the nomenclature, though, I want to real quickly talk about the cycloalkanes. So these are just some simple cycloalkanes. To name the basic simple ones, you just add the term cyclo to the name of the alkane with the correct number of carbons. So this has 3 carbons in it, and we learned that prop, P-R-O-P, means 3 carbons. So this is called cyclopropane. Okay, so the straight chain was propane. Now that it's cyclic, we call it cyclopropane. When we had 4 carbons was BUT, and so it would be butane if it was acyclic, but since it's cyclic, it's cyclobutane. This is cyclopentane, it has 5 carbons. This is cyclohexane, it has 6 carbons, cycloheptane, cyclooctane, et cetera, et cetera. And then you would be able to know, if I were to give you the term cyclohexane and you were trying to draw it, well, the cyclo tells you that it's cyclic and hexane tells you that there's 6 carbons. So 6 carbons is going to make a hexagon. So 1, 2, 3, 4, 5, 6. And then as far as how many hydrogens are on there, it would be CnH2n. So it would be C6H12. So again, you don't have to memorize the number of hydrogens. You need to know these formulas. Okay. So that's kind of the simple ones, naming them without any branching. Okay. When we start adding branches on here, or when we start adding branches to these chains, then it gets more complicated, and we're going to talk about that next. But those are your basic names without any branches of the acyclic and the cyclic. All right, now I'm going to talk about nomenclature, but I found this little video is helpful. It's just 2 minutes. If I can get my mouse to work here. Maybe. It looks like it has died. Okay, let's try a different mouse. I'm going to share a screen, and I'm going to play this little, I'm just going to play the first 2 minutes of this video. It certainly is longer. I'm going to assume you guys will be able to hear it. Make it bigger. If you can't hear it when I play it, you can send me a chat, because I can. Oh no, I can't see the chats. but I can see your images. So you could always unmute if you can't hear it, but I'm going to start it. I can't hear it, so I'm guessing you guys can't hear it. Oh, goodness. Details. Don't need that. That should go away. Let me stop the share a second. I think I know what I need to do. I need to change my microphone, probably to the computer. And let's see if that worked. I don't know how to make this thing go back away. Oh, well, I'm just going to play it. No, still can't hear it. Why didn't that work? Well, maybe I'm not going to play the video. That's too bad. Microphone is now the computer, so that should work, but it's not. Maybe the problem is my speakers. I know. Can you guys hear it when I played it? Did you start hearing some noise? Maybe it's just me who can't hear it because my speaker is my headphones. I should be able to hear it though. That's silly. No, you couldn't hear it. That's what I thought. To deal with this. Let's switch that to that and try one more time. Maybe it's the volume. Hold on a second. Where do I want to be for my volume? Way up there. Share. Oh. Share computer sound. Ha, I think I might have found it.
There's some of you out there taking chemistry and feeling a little bit like there's an international body whose job is simply to make your life more difficult, to force you to cram tons of information into your head, to suck all the wonder and excitement out of learning about how the world works.
Yeah, you can hear now, but it still seems low. I don't know if it's low for you guys, but I can barely hear it. So I was trying to see if there's a way I can up the volume on it. Oh, you guys heard it well. Okay, well, if it's plenty loud for you, I've already heard it before. So let's play it then.
Works at this beautiful fundamental level of chemicals. You are not actually imagining this. That organization actually exists. It's called the International Union of Pure and Applied Chemists, or IUPAC, and really they're looking out for your best interests. In just the same way that my mom was looking out for my best interests when she said that I couldn't go to the Violent Femmes concert with Megan Cross. And yeah, I hated my mom for like a full year after that, but she was right. That girl was trouble. So yes, you are allowed to hate IUPAC for changing the name of cinnamaldehyde, the aldehyde that makes cinnamon smell like cinnamon, to trans-3-phenylpropanol. Yes, they're sucking all of the fun out of the world, but trust me when I say, they're doing it for your own good. Cinnamaldehyde is a lovely name for a lovely aldehyde, just like cadaverine is a creative name for a rancid-smelling amine. Citronellol, angelic acid, vanillin, they're beautiful names, but there are tens of thousands of regularly used organic compounds, and we can't come up with pretty names for all of them. More important than that, though, there's no way to translate those names into chemical formulas. And IUPAC hates that. They're like, cinnamaldehyde, yeah, sure, it gives cinnamon its lovely smell, but we think that trans-3-phenylpropanol is way better of a name. name. And it actually is, because if I say trans 3-phenylprop-2-enol to somebody properly educated, they can just write down the chemical structure without even thinking about it. And that's like almost a kind of magic, where words go from relating to reality as we experience it, this chemical comes from cinnamon, so name it after cinnamon, to relating to the actual physical reality of the universe. And that's a magic worth knowing. IUPAC created a language that could be understood by everyone with minimal, even zero misinterpretation, and that's no easy feat. That's why, as we've discussed organic chemistry, when we start counting carbons, we make sure that the first thing named on the molecule is the lowest possible carbon. Not because there's something special about lower numbers, but because they had to make a rule, otherwise one chemical could be named 2 different ways. Let's go through the process of naming a chemical. It's a multi-step process. Step 1. How long is the carbon chain? 5 carbons will have pent, 7 sept, 3 prop, 1 meth. Don't feel weird if you have to look these up. I, for example, had no idea that a 23 carbon atom chain had the prefix tricosa until I looked it up just now. The only tricky thing here is to make sure you find the longest carbon chain. Sometimes a hexane can look like a pentane with an ethane sticking off of it. So now that you know your longest carbon chain, you've got your prefix, time to figure out the suffix. If there's nothing but hydrogen and carbon, your suffix just depends on whether you have any double bonds or triple bonds. You know these: propane, propene, propane.
All right. So I'm assuming you can still hear me. So I like that little introduction because it kind of lets you know that there's a reason why we have these naming rules, because you might start to get frustrated with these naming rules. We certainly will cover naming in pretty much every single chapter. How do we name the next type of functional group when it's attached to a molecule? And again, just as he described, there's a reason for it. With the proper name, any chemist or anyone who's educated in that way, so including you guys, even if you're not going to be chemists, could turn around and draw the structure simply from the name. And that's what we need to be able to do without having to memorize a bunch of structures. We can't memorize hundreds of thousands of compound structures. So we have a system that works out. So IUPAC, International Union of Pure and Applied Chemistry, as he explained, has a systematic method. We will use the most recent IUPAC conventions. They certainly change things sometimes. As a matter of fact, if you look at simply the older edition of our very own textbook, there's a couple of things that are different in the naming because the conventions changed. So just to let you know, we will use the most current conventions in our naming. Now, just a little aside, pharmaceutical drugs, a lot of you plan to be pharmacists. There's 3 names for those. There definitely is an IUPAC name because that will allow you to draw the structure of the particular compound of the drug. And then, of course, you know, there's generic names, so ibuprofen, and then there's a trade name, Advil or Motrin. But the IUPAC name for ibuprofen is 2,4-2-methyl-propanoic acid. A big mouthful to say, but I could sit down and draw that for you even if I'd never seen the molecule before, simply by knowing the naming conventions. Okay, so that's where it's important. We will not, in this class, look at generic or trade names. We'll use IUPAC names. Occasionally, we'll use common names, but when we do that, I will specify this is also a name that you guys should know and look for. And so let's look at naming the alkanes. So, the first thing is the parent name. And that indicates the number of carbons. So there we go. That's what I was trying to come up with earlier. So prop means 3, and then hex means 6, septa means 7. That's what they mean by the parent name. How many carbons are in, and notice it's the longest continuous chain. That's why it's really important that you can find those, so you can go back and to know what these parent names are. That's where that table comes in: meth, eth, prop, bute, penta, hexa, etc. Then the suffix will tell you the main functional group present. So the only one we're looking at right now is alkanes. So the main functional group is alkane, and so the suffix is ane. As we go through the other chapters, we will change the suffix. And then there's a prefix. And the prefix is going to tell you if there's any substituents, so branching or other things added to the molecule. And we need to know what is it, we need to know where it is, and how many of them there are. Okay, so the prefix is going to include all that information. So let's kind of start with that. So how would we name these substituents when they're alkane substituents, meaning they're substituents that only have carbon and hydrogen with single bonds? Because we just saw in the molecules we've looked at so far that we can have some side groups that are carbon and hydrogen. So carbon and hydrogen substituents bonded to the longest carbon chain are called alkyl groups, obviously coming from alkene, but since it's not the main molecule, we'll call it an alkyl group. They cause branching, and the alkyl group is formed by removing one hydrogen from the alkane. So methane would be CH4, but CH3 would be methyl. And now this has to be attached to something because that carbon needs 4 bonds. So it would, maybe it's better if I draw it this way. So then it would be attached to some other chain. We would have CH2, CH3 attached to some other longer chain. This is an ethyl group, etc. So we're still using the F and the meth and the prop and the bute, etc. But now instead of having an ANE ending, since it's a substituent on a longer chain, it has a YL ending. Okay, so that's what that means. So to name an alkyl group, you change the ANE of the alkane parent name to a YL ending. So again, as I just showed you, this becomes methyl. This becomes ethyl. Okay, so if these are either one of these are your substituents, that would be the substituent name. Now it gets a little more complicated when we get to 3 carbons because there's 2 different ways we can attach a group that has 3 carbons. So we start with propane. We're going to number this the number 1 carbon and this the number 2 carbon because that's going to make a difference when we attach it to the parent chain. So this is a longer parent chain, and if the end of the propyl group is attached to it, so it's attached to the number 1 carbon, or if a primary hydrogen is what we're losing when we attach it, then we call it propyl. But if it's a secondary hydrogen that we're losing when we attach it to the parent chain, we call it isopropyl. And again, it's out of focus, but this is isopropyl. So what does that mean? Well, we have to have a longer chain. So 1, 2, 3, 4, 5, 6, 7, 8, we'll say that. And then let's say we're attaching it to the end. So yeah, 1, 2, 3. It actually, that's a really, really bad example because I just messed up the longest chain. Let's stick with an example that's coming up, because if I make them up off the top of my head, it's possible I'm not going to come up with good examples. That was a bad example because I changed the length of the longest chain, so I didn't actually have a propyl group. I actually had a methyl group, so that was a bad example. We'll stick with the ones we got because it'll be faster. So if the 3-carbon alkyl group is attached to the parent chain on the end, it's a propyl, and if it's attached in the middle on the 2nd carbon, it's an isopropyl, and you need to memorize that isopropyl. You might just need to memorize what that group looks like. Okay. All right. And then what if it's a 4-carbon alkyl group that's attached? Well, now there is 4 different ways, or 4 different ways that can look. So now we have 4 different names for this. Okay, so we're back to the 1st or the 2nd carbon. So the 1st carbon, we would be removing a primary hydrogen to attach it to the parent chain. And the 2nd carbon, we would be removing a secondary hydrogen to attach it to the parent chain. So keep that in mind. So one way we can attach it to the parent chain is if on the 1st carbon, we remove a primary hydrogen and then link it to the carbon on the parent chain. This is simply called a butyl group. And it's just a normal straight chain 4-carbon chain, a butyl group. Now, if we attach it to the parent chain through the 2nd carbon, so we removed a secondary hydrogen to attach it, we call this a sec butyl group. And again, that's hard to see. SEC-butyl. And sec, which you can see right down here, stands for secondary. Oh, it didn't print well. So sec is short for secondary because we removed a secondary hydrogen in order to attach it. So that's where the term sec-butyl comes from. That'll help you with the memorization of it. Okay, and then we still have a simple 4-carbon chain like we did here attached, but now it's attached at the secondary carbon, and here it was attached at the primary carbon. Now we can rearrange the 4 carbons, and instead of having a straight chain, have a branched chain. Now it's attached at the primary carbon, but now it's not a straight chain. Instead, it's got a branch coming off, but it's still 4 carbons, 1, 2, 3, 4. We call this isobutyl. And there is not a dash here, which is actually really important because when we go to put this into a larger molecule, it's going to make a difference alphabetically if there's a dash or not a dash. Okay, so you might want to remember there's not a dash in isobutyl. And then there's one more way we can arrange these 4 carbons and then attach them to the parent. And that's this kind of thing. It kind of looks like, it always reminds me of a bird foot. Okay, but there's a tertiary carbon in the middle, and then there's these 3 methyl groups coming off of it, and then it gets attached to the parent chain at that tertiary carbon. Hence, this group is called a tert-butyl group because the parent chain is attached at a tertiary carbon. So we call it a tert-butyl group. And so that's, again, how you can remember that. So tert-butyl, the parent chain is attached to the tertiary carbon. Isobutyl, it's attached to the primary carbon, but it's got a branch, so isobutyl. Sec-butyl, the parent chains, there's no branching, but the parent chain's attached at a secondary carbon. And just butyl, you just got a normal straight chain and the parent chain's attached at the primary. All right, so we're not going to go on from there. We're not going to do pentyl because it just gets more and more and more complicated. So when we do these alkyl substituents, we're going to stick with methyl, ethyl, propyl, which includes isopropyl, and butyl, which includes sec-butyl, isobutyl, and tert-butyl. So those are the alkyl substituents that you need to know. All right, so now let's look at the steps you'd have to go through for naming these guys. So the very first thing you're going to do is find the parent chain. Now the parent chain is the longest chain, so sometimes you have to be careful. So this would be the step of finding the longest chain. So sometimes you have to count it more than one way. So if we started and counted straight across, we would have 8 carbons. If we started and counted down here, we would have 7 carbons. So in this case, this is my longest chain. So my longest chain is 8 carbons. When my longest chain is 8 carbons, then my parent name is octa. And since it's all single bonds, all carbon and hydrogen, it's octane. Now that's the parent and suffix. We haven't done the substituents yet. Okay, these are the same molecules, so this would also be octane. We counted it wrong. 7's not the longest, 8 is. This would be octane. That's the first step. The second step is to number the carbons in the chain. So you're going to start on one end and number across. But the question is, how do you know which end to start on? Do I start numbering here, 1, 2, 3, 4, 5, 6, 7, 8, or do I start numbering here, 1, 2, 3, 4, 5, 6, 7, 8? We are going to start on the side that, hold on, that's not where we are yet. Let's go here first. We'll come back to this one. We're gonna number the longest chain to give the first substituent the lowest number. Okay, so this, if I started numbering here, my first substituent I come to would be on number 2 carbon. If I start numbering here, the first substituent I would come to would be on number 3 carbon. So I'm going to number from this side because it puts my first substituent on the smallest number. And we have to have a rule for this. Otherwise, there would be 2 ways to name the same molecule, and that's not going to work for us. So we start numbering on the side of the chain that will put a substituent on the lowest number we can get it on. First substituent on the lowest number. Now, up here, back to this one, if you can make 2 chains of equal length, pick the chain with more substituents. So 1, 2, 3, 4, 5, 6, 7. This is a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. This is also a 7-carbon chain. So I can number this either way, and I still am going to have heptane. So how do I know which one to do? This one is going to give me one substituent. This one is going to give me two substituents. This is going to be the correct option because it gives me more substituents. The reason you want that here to name substituents when we have smaller numbers of substituents or smaller substituents like methyl, ethyl, or propyl. And it's much harder to name them when we get to pentyl or hexyl. So we want our substituents to be small groups. And that happens more likely when you have more substituents instead of less. All right, next rule. If the first substituent is the same number from either end, then you're going to find your second substituent and make sure it's on the lowest number. So we have to take everything into account. So notice no matter which end I start from, these two methyl groups would be on the second carbon. 1, 2, 1, 2. So that doesn't help me. This rule up here doesn't help me in that case. So now I need to look and see where my second substituent would be. If I started number on this side, the second substituent would be on number 3. If I started numbering from this side, the second substituent would be on number 4. 3 is smaller than 4. So this one is the correct one. Okay. All right. I'm going to finish these rules here. So the next rule is when the chain has the same numbers from either end. So in other words, if I start on this side, my first substituent's on the 3 and my second substituent's on the 5. If I start on this side, my first substituent's on the 3, my second substituent's from the 5. So it's like, well, what do I do then? No matter which way I start, I get a 3 and a 5. When that's the case, then you want to assign the lower number alphabetically. So you're looking at the names of your substituents now. Whichever one comes first alphabetically, you want to put as the first substituent. So you have an ethyl group and you have a methyl group. Alphabetically, E is before M. So we want the E substituent, the ethyl substituent, on the smaller number carbon. So starting from this side, the ethyl group's on the number 3. Starting from this side, the ethyl group's on the number 5. This is the correct one because it puts the first alphabetical substituent on the smaller carbon number. Okay, I know there's a lot of rules. You have to practice these things. The reason there's a lot of rules is because we end up with molecules like this and there can only be one way to name them. If there's 2 names, it's going to mess everybody up. So there's got to be a rule to cover every single possible scenario you could come across. Now, when we're talking about alphabetizing, notice this right here. When we alphabetize substituents, we ignore tert and sec. That's what it means by ignore the prefixes. But we don't ignore iso. So isobutyl or isopropyl starts with an I. Tert-butyl or sec-butyl starts with a B. All right, so that's why these have dashes. Isobutyl doesn't have a dash. Isopropyl doesn't have a dash. That's why I said you need to keep in mind which has dashes and which do not, because one is a proper way to write it and one is not. Now, what if I have more than one of the same substituent? Then instead of saying methyl, 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 if I have 3 methyl groups, I'm going to say trimethyl. So I'm going to combine them all together and use these prefixes to indicate how many. So you could have dimethyl, you could have trimethyl, you could have tetramethyl. If you have 4 methyl groups on the same molecule, you could have diethyl, you could have dipropyl, you could have diisopropyl, anything like that. Okay, so we're going to group them together and so that I only have to write it once. Then the other thing that needs to be kept in mind is, so now we know how to do the parent name and the suffix and the substituent names and how to number the longest chain. But how do I tell what location, which carbon the substituent is on? We're going to actually write the number before we write the substituent name. There must be one number for each substituent when you go to write the name. And then we're going to separate numbers if there's more than one number in a row by commas, and we're going to separate the numbers from the letters and the name with hyphens. So we're going to put all that together and look at this example here. So we're going to number this. We're going to count the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 8's the longest. So we know that we've got octane. We're going to write that down. Then we're going to look at our substituents. I have a methyl, I have an ethyl, I have a methyl. If I start counting from this side, my first substituent's on a 2. If I start counting from this side, my first substituent would be on a 3. 2 is less, so I'm going to start counting from this side. 1, 2, 3, 4, 5, 6, 7, 8. I would write them out. Write them, draw them out. You'll have plenty of room on your tests and quizzes and in your homework. Write the numbers out so you don't forget. Okay, so this methyl's on a 2, this methyl's on a 6, this ethyl's on a 5. Now I need to figure out what do I write first when I go to write out the substituents. I write them in alphabetical order. So I'm going to, the ethyl, E comes before M. So I'm going to put the ethyl first, and I need to put what number it's on. So it's on the number 5. So 5, I'm going to do this. I've got octane, and now I have 5-ethyl. Okay. Now I've got 2 methyl groups, so I'm actually going to combine them together and call them dimethyl. But I have to include a number for each one. So it's on, this one's on a 2 and this one's on a 6, so it's going to be 2, 6 dash dimethyl, and I have to put a dash here between a letter and a number. And then octane goes on the end. So this molecule is called 5-ethyl 2,6-dimethyl octane, just like it says right there. Now, when you go to write these names out, you may have to write pieces and then put it all together after you get all the pieces figured out. Okay, so when you're writing on a test, you might need to write the parts out to the side, and then when you write your final name all laid out, then you can put like a box or circle it so I know exactly which name you want me to grade. Okay, because you might have to write the pieces down before you can put the whole thing together. Questions? Everyone's pretty quiet. Any specific questions on that? It seems like a lot, and maybe it is a lot, but it's just going to take a lot of practice is what it's going to take. Okay, why don't I apply it to a couple of these examples? I know we're slightly over an hour, but why don't I go ahead and apply it to 2 examples before you guys go so that you can at least see it in action while it's fresh in your mind. And then we'll talk about naming cycloalkenes, which would be the next thing. We'll do that in class on Monday. So, but let me apply this to the, I'll just do these first 2. So, and they're lettered wrong. So I thought I have these okay in the PDF, but apparently I've messed these up. So we'll just, this first one. So the first thing I have to do is find the longest chain. So I'm going to start here and start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 if I go that way. Obviously this is longer than that, but is this possibly longer? 1, 2, 3, 4, 5, 6, 7. Nope. 9 is going to be my longest chain. So I have 9 carbons. So that right there tells me nona is 9. So that tells me I have no name. Okay, that's my parent name and my suffix. That part's easy enough as long as you can find the longest chain. So now I need to look for my substituents. I have a substituent here, and I have a substituent here. If I start numbering on this side, my first substituent, 1, 2, 3, 4, 5, would be on the number 5 carbon. If I start numbering here, my first substituent would be on the number 3. So I'm going to start numbering here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, you should just write the numbers in. It can save you from messing up later. So now I see I have a 1-methyl. I'm going to write this down here. I have a 3. The methyl's on a 3. So I have a 3-methyl. And then this, if you go back over, remind you what this is. This is that little chicken foot thing, and we call that tert butyl. So you're going to have to know that. You have to memorize that. When it looks like a little chicken foot, it is tert-butyl. And you can actually write that two ways. You can just write out tert-butyl, or you could just do lowercase t butyl, and it means the same thing. As a matter of fact, if you see t-butyl, that means tert-butyl. It's just an abbreviated way. And we see it's on the number 5 carbon, so 5-t-butyl. So we're going to cross that off because we're going to use these two versions. So this is what I have. I have to put these in alphabetical order. This is an M. This is a B because we don't use the T in the tert-butyl when we alphabetize. So the B is going to become first. So when I go to write this whole name, it's going to be 5-t-butyl, and then dash 3-methyl, and then no name. So 5-tert-butyl, 3-methyl nonane. And there's no dashes or spaces between the methyl and the nonane. Okay, so that just runs together. So this would, all right, let me do one more. Actually, we're going to do the one on the end because the second one's yeah, they're about the same. So we'll do the one on the end. We'll do this one. Okay. All right. So I need to find my longest chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Either way, it doesn't matter. So I can start it with either one of these and I'll get 7. So this has 7 carbons. So it has 7 carbons is hepta, and then it's an alkane, so heptane. So that's my parent name suffix. Then I look and see, okay, well, I've got a substituent here and a substituent here. So I have 2 substituents. They're both methyls. Since I have 2 methyls, I would call that dimethyl. And then I need to figure out what numbers they're on. Well, if I start numbering here, this is on a number 2. If I start numbering here, 1, 2, this is on a 4. So 2 is smaller than 4. So 1, 2, 3, 4, 5, 6, 7. So it's on a 2 and a 4. So 2, 4 dash dimethyl. So when I put this together, I'm going to have 2, 4 dash dimethyl heptane. Okay. All right. Questions on either one of those? All right. So you do need to go with the other direction. Given the name, draw the structure. That's usually easier. It's usually a lot easier. There are a couple examples here. Why don't we wait since we're already at 8:10 and we'll do those on Monday. So the plan for Monday is as long as we have class, because goodness knows it could snow again. I think we might actually, they might already be predicting, but we'll see. So if we have class, we will start from here. And we'll look at how we go back the other way. We'll look at how we name cycloalkanes, and then we'll keep going forward from there. And then I'll teach for an hour and 15 minutes, which is our normal lecture time. And then at 6:45, I'll stop. And then you guys can do a 15-minute break to use the restroom or whatever you need. And then we'll start the exam at 7. And you'll have until 9:50 to complete the exam. Okay, so that's our plan for Monday. Your homework, chapter 2 and 3, will be due Monday. So just bring that with you when you come. And then you also do have that worksheet due from the lab we did on Monday. So the worksheet handout I gave you, it is actually needs to be turned in online. So there are instructions for that. You go onto Canvas and turn it in there. Okay, and if you run into any problems, you can always ask me Monday night because it's not due till 11:55 p.m. Monday. Okay, so if you try to submit it through Canvas over the weekend and you run into any issues, you can certainly email me, but you can also ask me in person on Monday because, but ask me before class or during the break because once everybody's taken the exam, we don't want to interrupt anybody. And so you don't want to hang out and wait until 9:50 if you're not going to take that long. Okay. Any questions before I sign off? Will we know more about lab schedule Monday? Yes, I'll make the decision in the next day or so. I have an idea of what I think that I'm going to do, but I want to
kind of piece it together and sort of write it all out before I say for sure of what I think I'm going to do. But yes, I will definitely, for sure by Monday, I'm hoping to send you an email sooner about what's going on with your lab schedule, what we'll do on Wednesday for lab. Any other questions? Okay. Yep. So I think that's it. So we'll sign out. And lucky you, you get a few more days to study for your exam. So you guys should all be getting 100% on that exam. And have a good night. Have a good weekend. Stay safe and stay warm. Bye.